Welcome to The Whispering Scientist. If you're settling in now, let your shoulders drop and your breath lengthen just a little, because we're not rushing anywhere tonight. We're simply looking up, together, at that pale river of light that sometimes appears when the darkness is patient enough to let it through. Welcome to Science for Sleep, this quiet corner where curiosity slows down and science takes its time. You've probably seen it in photographs from space telescopes or long exposure shots that capture its sweeping arms. But perhaps you've also glimpsed it with your own eyes, stretching across a dark countryside sky or arching over a mountain horizon. That gentle band of light, too faint for city streets to allow, is the Milky Way, our home galaxy. The vast collection of stars and dust and invisible matter that holds us all together. But how big is it really? That's the question we'll drift through tonight. Before we venture into spirals and distances, let me ask you something simple. Where are you listening from this evening? What do the stars look like where you are? For some, they're crisp pinpricks in a desert night. For others, they're softened by city haze or hidden entirely behind electric glow. Yet no matter how clear or veiled your sky, you're inside the Milky Way right now. You can't step outside it for a complete view. You can only look outward and piece together its story from where you sit, like trying to sketch your neighborhood's shape while standing on one of its streets. If this gentle exploration helps you unwind, I'd be grateful if you considered subscribing. It helps this calm corner reach others who might need a peaceful companion for their thoughts. And if you're already here often, thank you for joining this journey. Now take a slow breath and let your mind stretch beyond its usual boundaries. The Milky Way is our familiar address, but it's also incomprehensibly vast, woven with mysteries, and perfect for contemplating as we drift toward rest. Imagine holding a map of everything you know: your street, your town, your country, the entire Earth, even our solar system. Now zoom that map outward until every star visible in your sky is included. That's the Milky Way, but this description barely touches its true scale, because the numbers involved are so large that everyday measurements simply dissolve. When we ask how big the Milky Way is, we face an extraordinary challenge. We're trapped inside it like trying to measure your house while blindfolded. You touch walls, count steps, feel around corners, but never see the complete shape. Astronomers encounter the same puzzle with our galaxy. They can't photograph it from outside. Instead, they measure light, map star positions, and build models, slowly sketching something so enormous that light itself needs over 100,000 years to cross from edge to edge. 100,000 light years. That's the diameter astronomers give for our galaxy. But what does a light year mean? It's not time but distance. The span light travels in 1 Earth year. Light moves at nearly 300,000 kilometers every second, faster than anything in daily experience. In 1 second, light could circle Earth more than 7 times. Multiply by 60 for a minute, 60 again for an hour, 24 for a day, then 365 for a year. You reach almost 10 trillion kilometers. That's 1 light year. Now stretch that by 100,000. That's the Milky Way's width. Numbers this large stop feeling like numbers and become whispered ideas instead. Picture our Sun, then imagine its nearest neighbor, Proxima Centauri, 4.2 light-years away. Traveling there with today's fastest spacecraft would take tens of thousands of years. That's just our tiny local neighborhood. To reach the galactic center requires multiplying that distance by 25,000. The galaxy's far edge lies twice that distance beyond. Yet within this overwhelming span, everything moves with purpose. Stars orbit smoothly, gases swirl in ancient patterns, and invisible dark matter binds it all in a cosmic dance. Right now, without feeling it, you're part of that motion. The ground beneath you, your room, everything you know orbits the galactic center at nearly 828,000 kilometers per hour. You feel none of this because everything nearby travels together like passengers on an enormous silent ship. It's a strange realization. You're not sitting still. You're riding the solar system as it circles the Milky Way like a small boat in a vast harbor. Yet everything feels calm, steady, peaceful. Perhaps that's the magic of pondering galaxies at bedtime. It reminds you that daily worries, schedules, and rushing exist inside something incomprehensibly larger, steady, and ancient beyond human timescales. This vastness wasn't always known. For centuries, that faint streak overhead was pure mystery. Was it cloud, fire, the edge of creation? Ancient peoples wove it into stories of spilled milk, scattered stars, pathways for souls. Only when glass lenses revealed its true nature did the questions deepen. If that glow was countless distant suns, how many? How far? And where exactly were we among them? Tonight, we'll trace that journey of discovery, from the first myths to the measurements that revealed our cosmic address. But for now, simply rest in this opening wonder. The gentle band you might glimpse overhead isn't decoration on the sky. It's the cross-section of an entire galaxy, seen from within, and you're floating inside its embrace. The gentle river of light we glimpsed in our first question has always been there, patient and glowing long before anyone thought to measure it. To understand how we discovered its true vastness, we must first step back into deeper darkness, into nights when that pale band was not a faint suggestion, but a commanding presence. Imagine yourself thousands of years ago, sitting by dying embers at the edge of an endless plain. The only light comes from your fire and the stars themselves. No cities exist, no electric glow to thin the heavens. What fills your vision is a sky crowded with more points of light than most of us see in our entire lives, and slicing across them all. A luminous river that seems too wide and soft to be made of individual stars. That was the Milky Way, though no one called it that yet. It was simply there, a celestial mystery painted above every culture that ever looked up. When you see it in such conditions, far from artificial light, it becomes impossible to ignore. It arcs across the heavens like a glowing backbone, sometimes hazy, sometimes sharp, depending on where you stand on Earth. For ancient observers, this sight was more than beautiful. It demanded explanation. Why should the sky have this streak unlike anything else in nature? Clouds move, the moon changes phases, planets wander slowly among the stars. But this river of light remained fixed, permanent, stretching the same way across seasons. It seemed eternal, so it became wrapped in myth and meaning. The Greeks imagined milk spilled from the breast of the goddess Hera when the infant Heracles pulled away, giving our galaxy its familiar name. The drops became stars, a permanent record of divine drama etched across the heavens. To them, the sky wasn't separate from daily life, but woven together with human affairs and powerful events. Travel eastward and the stories shift. In ancient China, the Milky Way became the Silver River, with a tale of the cowherd and weaver girl, lovers separated across its width who could meet only once yearly when magpies formed a bridge. This legend, still celebrated today, gave the galaxy emotional resonance. It wasn't merely a stripe of light, but a river of longing, of distance and reunion. When people looked up, they saw a love story played across eternity. In southern Africa, some traditions called it the backbone of night, a structural beam holding the sky together like a cosmic spine. Aboriginal Australians wove even more sophisticated interpretations, reading not only the bright band but the dark lanes within it. They traced an emu in the dust clouds, saw smoke from ancestral fires, followed paths of spiritual beings crossing the heavens. The darkness wasn't emptiness, but story, cut from the light itself. Across the Pacific, Polynesian navigators transformed the galaxy into a practical tool. The Milky Way became a map spread above their heads, its orientation revealing direction and position among islands scattered across thousands of miles of ocean. Imagine being at sea with no land in sight, only waves and stars. The galaxy would stretch above like a compass, steady and reliable, telling you where you were and where you needed to go. In the Americas, the band took on forms tied to land and spirit. The Lakota spoke of it as the spirit trail, the path souls traveled to the afterlife. The Cherokee told of a dog who stole cornmeal and scattered it across the sky as he ran, leaving a pale trail that would never quite be swept clean. Among the Maya, it became a world tree connecting underworld, earth, and sky. The Inca called it Mayu, a celestial river mirroring earthly waterways, its seasonal movements tied to rains and planting cycles. What strikes you about these diverse interpretations is their shared recognition. They all treat the Milky Way as singular, different from scattered stars, steady in its arc, impossible to ignore. They also reveal something beautiful about how minds meet magnitude. Confronted with something beyond counting, we reach for the close at hand. Milk and rivers, spines and pathways, animals and ancestors. By bringing the unreachable into familiar shapes, people could carry it, teach it, pass it to children around fires or along shorelines while surf whispered in the dark. These stories weren't just entertainment. They were knowledge systems teaching lessons, marking seasons, explaining cycles. For agricultural societies, the galaxy might guide planting times. For nomadic groups, it provided orientation. For spiritual traditions, it connected realms. The Milky Way became practical law and cosmic compass at once. Despite their differences, certain themes recur. Rivers appear again and again. Pathways emerge repeatedly. Structural elements like backbones and bridges connect worlds together. When people tried to understand the Milky Way, they reached for metaphors of connection, of structures linking realms. Perhaps this intuition was natural. The galaxy itself connects countless stars, so seeing it as a bridge or river sensed, even without science, that it bound the cosmos into wholeness. Consider the profound effect of seeing it every clear night. Without electric light, darkness wasn't absence, but presence, half of each day filled with reliable patterns. The Milky Way's constancy would mark months and seasons, orient sleep and travel, set the tempo of stories told and retold. That persistence invited both myth and, eventually, curiosity about its true nature. For thousands of years, the galaxy remained beautifully unknowable, a mystery that forced people to think beyond themselves, to accept things larger and more permanent than daily life. The steady glow wasn't threatening but undeniable, always there like a patient teacher waiting for the right questions. And slowly, as human curiosity kept its gentle pressure, those questions began to form. Was that band cloud or fire? Smoke or stars? What lay inside that brightness, and where among it might we live? The myths carried us to the edge of such wondering and set us down softly. From there, when the right tools finally appeared, another kind of seeing would begin. The myths had carried us to the very edge of wondering, each story a bridge between human imagination and cosmic mystery. But for all their beauty, these ancient tales could only reach so far. The eye alone, however patient, however careful, could not pierce the veil of that gentle river overhead. Then in the early years of the 17th century, something extraordinary happened. Humans learned to bend glass in just the right way, creating devices that brought distant objects startlingly close. At first, these contraptions were curiosities for watching ships on horizons or birds across meadows, but it was only a matter of time before someone thought to lift one toward the stars. That simple gesture changed everything. The telescope arrived quietly, almost accidentally, emerging from Dutch lens grinders who discovered that combining curved pieces of glass could magnify distant scenes. Word of this marvel spread across Europe like ripples on water. By 1609, an Italian mathematician named Galileo Galilei had heard the rumors and built his own version, improving the design until objects appeared many times larger and clearer than before. His instrument was crude by our standards, with lenses that distorted edges and magnifications that seem modest today. But compared to the naked eye, it was nothing short of magical. Imagine that first evening, when Galileo turned his telescope skyward. The moon, which poets had praised as a perfect silver disk, suddenly revealed itself as a world of mountains and valleys, shadows creeping across crater rims as sunlight struck from different angles. The smooth perfection that philosophers had insisted must exist in the heavens crumbled into beautiful, rough reality. Then came Jupiter, no longer a simple wandering star, but a tiny disk accompanied by 4 faithful companions, bright points that shifted position night after night in their own celestial dance. Here was proof that not everything in the universe circled around Earth. But when Galileo aimed his telescope at the Milky Way, the transformation was even more profound. That familiar band of soft light, the gentle river that had inspired countless myths, began to dissolve before his eyes. What had always appeared as continuous mist revealed itself as something far more extraordinary. The smooth glow broke apart into countless individual points of light, stars so faint and numerous that they had blurred together into that familiar streak. Galileo struggled to find words for what he saw, finally describing it as a congregation of innumerable stars, far more than anyone had ever suspected. Think of that moment of revelation. For thousands of years, people had looked at the Milky Way and seen unity, a single celestial feature painted across the heavens. In one night, through a simple tube of glass, that unity dissolved into multitude. The river became an ocean. The path became a population. What had seemed like divine brushwork was revealed as countless distant suns, each one perhaps like our own, scattered across unimaginable distances. It must have been both thrilling and overwhelming, like watching morning fog lift to reveal not empty fields, but a vast city stretching to every horizon. This discovery rippled outward in ways Galileo could never have anticipated. If the Milky Way was made of stars, then how far away must they be? How many more lay hidden beyond his telescope's reach? And if there were so many stars, might some of them have their own worlds, their own stories unfolding in the darkness? The questions multiplied faster than answers, each observation opening new mysteries while solving old ones. Other astronomers quickly followed Galileo's lead, building larger telescopes and peering deeper into space. Across Europe, instruments improved and discoveries accumulated. The Milky Way revealed more layers of complexity with each advancement. Fainter stars emerged from the background. Dark lanes of cosmic dust became visible, breaking the glow into channels and streams. What had once appeared uniform was shown to be structured, varied, alive with detail, invisible to eyes alone. Yet the telescope also taught humility. Every improvement revealed that previous understanding had been incomplete. The instrument showed more, but it also made the universe more puzzling. Those cloudy patches scattered across the sky, the nebulae that remained fuzzy even under magnification. What were they? Gas clouds within our own system or distant star cities beyond? The telescope had opened a door to deeper knowledge, but that door revealed corridors stretching far beyond what anyone had imagined. For people of that era, looking through a telescope must have felt like stepping into another realm. You would lean over the eyepiece and suddenly inhabit a universe far richer and stranger than the one you had known moments before. The moon became a landscape. Jupiter became a system. And the Milky Way, that gentle companion of every clear night, transformed into an ocean of suns. The experience was both wonderful and disorienting, expanding the boundaries of the possible while challenging every assumption about humanity's place in creation. The cultural impact was profound but gradual. Artists began painting lunar mountains on their canvases. Poets wrote of oceans of stars. The idea that the heavens had geography, texture, and complexity made them feel both more distant and more real. The night sky was no longer purely symbolic, but had become a landscape you could explore, at least with your eyes and instruments. This revolution in seeing set the stage for everything that followed. Once the Milky Way was revealed as a system of stars, the next question became inevitable. If we live among these countless suns, where exactly do we fit within their arrangement? Are we at the center of this stellar city or somewhere else entirely? The telescope had shown us the population. Now came the harder task of mapping our place within it. Galileo's telescope had dissolved that gentle river of light into countless individual stars, transforming myth into multitude. But this revelation immediately presented a new and profound puzzle. If the Milky Way was indeed an ocean of distant suns, where exactly were we within this vast stellar architecture? Were we standing at the edge of this cosmic city, looking inward at its lights? Or were we somehow embedded within it, surrounded by the very stars we sought to understand? The question seems simple now, but it would take centuries to answer, and the discovery would humble us once again. Imagine standing deep within an ancient forest on a misty morning. At first, you might think you're at the forest's edge, looking into a wall of trees that stretches away from you. The fog makes distant trunks fade into grey obscurity, and you can only see clearly for a short distance in any direction. You might count the trees visible around you and assume you're surveying the forest from outside. Only gradually, as you walk and observe more carefully, does the truth become clear. You're not at the edge looking in. You're deep within the forest itself, with trees extending in every direction, their forms disappearing into mist no matter which way you turn. This was precisely the challenge that confronted astronomers after Galileo's discoveries. We were lost in a forest of stars, trying to map something we could never step outside to see. In the late 18th century, William Herschel and his devoted sister Caroline took up this seemingly impossible task. Night after night, through the cold darkness, they pointed their massive homemade telescope in different directions and began what Herschel called star gauging. They would divide the sky into small sections and carefully count every star visible in each patch, slowly building a census of the heavens. Their method was both brilliant and painstaking. If more stars appeared in one direction, perhaps the galaxy extended farther that way. If fewer stars were visible, perhaps they were looking toward an edge or boundary. After years of meticulous observations, Herschel sketched one of the first maps of our stellar home. His drawing showed a flattened, lens-shaped system with the sun positioned reassuringly near its center. It was a monumental leap of reasoning. The first time anyone had proposed that we weren't merely observing the Milky Way from outside, but were actually embedded within its structure. Yet Herschel's map contained a hidden flaw, something he couldn't possibly have known. Between the stars hangs an invisible veil, vast clouds of cosmic dust that absorb and scatter starlight like fog in our forest metaphor. When Herschel looked in certain directions, he wasn't seeing fewer stars because the galaxy ended there. He was seeing fewer stars because his vision was blocked by these unseen clouds. The dust created false boundaries where none existed, making our position appear more central than it truly was. Still, Herschel's fundamental insight was revolutionary. We are indeed inside the Milky Way, surrounded by its stars in every direction. That familiar band of light overhead isn't a distant decoration painted on the sky. It's the cross-section of our own galactic home, viewed from within. When you look toward Sagittarius on a summer evening, you're gazing inward toward the galaxy's crowded heart. When you turn toward Orion in winter, you're peering outward through sparser regions toward the edge. Our entire view of the night sky is shaped by this inside perspective. The realization that we live within the Milky Way was both thrilling and humbling. Every star visible to your eyes, every constellation, every glowing patch of nebula was part of our cosmic neighborhood. We weren't detached observers studying a distant system. We were residents, inhabitants, integral parts of the very structure we were trying to understand. The night sky wasn't decoration, but landscape, stretching around us in 3 dimensions. The breakthrough that revealed our true position came in the early 20th century through the work of Harlow Shapley. Instead of counting stars in the dusty disk, he turned his attention to globular clusters, ancient spherical swarms of stars that orbit high above and below the galactic plane like lanterns hung in the darkness. By measuring distances to these clusters and plotting their positions, Shapley made a startling discovery. They weren't centered on the sun. Instead, they formed a great halo whose center lay far away in the direction of Sagittarius, tens of thousands of light-years from us. In one careful observation, astronomy completed another Copernican revolution. Not only was Earth not the center of the solar system, but the sun was not the center of the galaxy either. We lived in the galactic suburbs in a quieter district far from downtown. The band of light we see is brightest toward Sagittarius because we're looking inward toward the crowded center, and thinner in other directions because we're looking outward through the disk's edge or up and down through its thinner dimensions. And as you contemplate this placement, remember that you're not standing still in this cosmic forest. You're part of that motion we discovered in our previous wandering, carried along at 828,000 kilometers per hour as our sun orbits the galactic center. The journey is so vast that one complete circuit takes 225 million years, but because everything nearby travels together, it feels perfectly calm. You're riding through the galaxy like a passenger on a smooth, silent ship, seeing the forest slowly change around you as eons pass. From our position within this stellar forest, the next challenge became clear. If we couldn't step outside to see the whole, how could we map the pathways that wind through it? How could we trace the spiral arms that curl outward from that distant center? The tools would need to become more subtle, the methods more ingenious. But first, we had found our place, inside the dance, part of the structure, citizens of a galaxy we were only beginning to understand. We had discovered ourselves lost within that stellar forest, citizens of a galaxy we could never step outside to photograph. Shapley's globular clusters had revealed our humbling truth. We weren't at the cosmic center, but lived in the galactic suburbs, tens of thousands of light-years from downtown. Yet knowing we were embedded within the Milky Way only deepened the mystery. How could we possibly map its neighborhoods and trace its pathways when we were trapped inside, like trying to sketch the layout of an entire city while blindfolded on a single street corner? The greatest obstacle wasn't our position, but something far more subtle. Between the stars hangs an invisible veil, vast clouds of microscopic dust particles that absorb and scatter starlight like fog in our forest metaphor. This interstellar dust had fooled Herschel's careful star counts, creating false boundaries where only opaque walls existed. When he looked in certain directions and saw fewer stars, he wasn't glimpsing the galaxy's edge, but staring into cosmic curtains that blocked his view completely. To map our true galactic address, astronomers needed to find ways to see through this invisible barrier. The first breakthrough came from recognizing that stars themselves could become measuring sticks. Hold your finger at arm's length and blink one eye, then the other. Your finger seems to jump against the background. Astronomers use Earth's entire orbit as the baseline for this same trick, called parallax. By measuring how nearby stars shift slightly against distant ones over 6 months, they could calculate precise distances. For the closest stars, this tiny wobble opened the first steps of a staircase into the galaxy, though it couldn't reach very far through the dusty depths. Beyond those first steps lay darkness that parallax couldn't penetrate. Astronomers needed cosmic lighthouses scattered deeper into the Milky Way, beacons whose true brightness they could know. The answer came from patient observers studying pulsing stars. Henrietta Leavitt discovered that certain variable stars called Cepheids keep perfect time with their own brightness. The longer their pulse period, the more luminous they truly are. By comparing this intrinsic brightness to how dim they appeared from Earth, astronomers could calculate their distances. These stellar heartbeats became yardsticks threaded through our stellar forest, extending the map thousands of light years farther. But even with these standard candles, the cosmic fog remained impenetrable in many directions. The solution required entirely new eyes, instruments that could see beyond visible light. Infrared telescopes detect longer wavelengths that pass more easily through dust, revealing hidden stars and gas clouds deep within previously obscured regions. When astronomers built these infrared eyes, regions that appeared blank in visible light suddenly bloomed with stellar populations, especially toward the galactic center, where the dust veil is thickest. The most revolutionary breakthrough came after World War II with radio astronomy. Scientists discovered that hydrogen atoms, the universe's most abundant element, emit radio waves at a very specific wavelength. These radio whispers penetrate dust clouds completely unhindered, like switching from a flashlight to radar in thick fog. By tuning giant radio dishes to this hydrogen frequency, astronomers could finally map gas distributions across the galaxy's entire span, seeing through every dusty obstruction that had limited previous generations. What radio telescopes revealed was breathtaking. The hydrogen wasn't spread evenly but concentrated along sweeping spiral arms that curved outward from the central regions. These arms appeared as bright ribbons in radio maps, tracing graceful patterns that immediately suggested the galaxy's true architecture. For the first time, astronomers could glimpse the Milky Way's spiral structure from within, like hearing a river's course through dense forest by following the sound of flowing water. To anchor this emerging map, they needed an unmistakable center. In Sagittarius, buried behind thick dust, a compact radio source blazed steadily. Infrared observations revealed stars racing around an invisible mass there, whipping through tight orbits that pointed to a single location, the galaxy's heart. This anchor, later named Sagittarius A star, fixed the map's origin and gave astronomers a reference point for measuring everything else. With the center known and radio waves piercing the dust, our galactic address finally emerged. The Sun orbits roughly 26,000 light-years from that hidden heart, positioned comfortably between the crowded core and the sparse outskirts. Our path lies within a modest spur called the Orion Arm, tucked between larger spiral highways like living on a quiet side street in a vast cosmic city. We sit slightly above the galaxy's midplane in a disk only a few thousand light-years thick compared to its 100,000 light-year span. Each new instrument added layers to this understanding. Space telescopes refined parallax measurements for billions of stars. Infrared surveys revealed the galaxy's center in unprecedented detail. Radio observations traced magnetic fields threading through space. The invisible had become visible through human ingenuity and patience, transforming that gentle river of light overhead into a detailed map of our galactic neighborhood. From our single vantage point within this vast system, we had learned to read subtle clues that revealed its architecture. We found our address in the cosmic city, a suburban location in the Orion Arm, embedded within a grand spiral stretching from edge to edge. But knowing where we live only raised new questions. What are these spiral pathways like up close? How do they shape the galaxy's life and our own place within its turning arms? We had found our galactic address through radio waves that pierced the cosmic dust, revealing our quiet suburban location in the Orion Arm. But those same radio telescopes had uncovered something even more extraordinary. The hydrogen gas wasn't scattered randomly through space, but concentrated along sweeping curves that spiraled outward from the galactic center like cream stirred slowly into coffee. For the first time, we could glimpse the Milky Way's true architecture from within, a grand spiral galaxy with elegant arms threading through the darkness. Yet these arms weren't the solid structures you might imagine. There's something far more subtle and beautiful, patterns in motion, waves of density that have persisted for billions of years, while individual stars drift through them like travelers on cosmic highways. Think of driving through heavy traffic during rush hour. Cars move at different speeds, changing lanes, entering and exiting, yet the traffic jam itself maintains its shape and position. Vehicles flow through the congestion while the pattern remains. The Milky Way's spiral arms work similarly, creating what astronomers call density waves, regions where matter crowds together temporarily before dispersing, maintaining the galaxy's distinctive swirling form even as stars complete many orbits around the center. Our galaxy possesses 4 major arms sweeping outward like the limbs of a vast pinwheel. The Perseus arm stretches in the direction of that constellation, while the Scutum Centaurus arm curves through those southern star patterns. The Norma arm and Sagittarius arm complete the grand design, each one a cosmic boulevard thousands of light-years wide. Between these major highways lie smaller structures and spurs, including our own Orion arm, which branches modestly between the larger thoroughfares. If the major arms are busy downtown avenues, we live on a quieter residential street, still part of the galactic city but away from the heaviest stellar traffic. Each arm tells an ongoing story of birth and renewal played out on incomprehensible scales. As vast clouds of hydrogen gas drift into these density waves, they compress and heat up, triggering the gravitational collapse that ignites new stars. The arms blaze with blue-white giants, massive young suns that burn brilliantly but briefly, lighting up their neighborhoods with intense radiation before exploding as supernovae. These stellar fireworks scatter heavy elements into space, enriching the gas for future generations of stars and planets. The arms are cosmic nurseries and recycling centers simultaneously, places where the galaxy renews itself in endless cycles of creation and dispersal. From our embedded position within the Orion arm, we can glimpse this creative process at work in our own neighborhood. The famous Orion Nebula, visible to your naked eye as a fuzzy patch in the hunter's sword, is one such stellar nursery where new suns are condensing from gas and dust. The Eagle Nebula with its towering pillars of creation, the Lagoon Nebula with its pink hydrogen glow, these are windows into the galaxy's ongoing birth processes happening right around us. Yet from our street-level perspective, we cannot see the full spiral pattern directly. We're like residents trying to map their city's layout from a single intersection, catching glimpses of the overall design, but never the complete picture. When you look towards Sagittarius on summer evenings, you're gazing along one of the spiral arms toward the galaxy's center, which is why the Milky Way appears brightest in that direction. When you turn toward Orion in winter, you're looking outward through the arm structure toward the galaxy's edge, where the glow appears thinner and more scattered. The spiral arms also shape our cosmic environment in ways both subtle and profound. As our solar system completes its 225 million-year orbit around the galactic center, we drift in and out of different arm regions over geological timescales. Sometimes we find ourselves in the quiet spaces between arms, where star formation is less active and cosmic radiation levels are lower. Other times we plunge deeper into the arms themselves, encountering more massive stars, more frequent supernovae, and higher background radiation. Some scientists speculate that these passages might influence Earth's climate or even biological evolution, though such connections remain actively debated. What's certain is that the arms organize the galaxy's evolution. Without them, star formation would still occur, but more randomly, less efficiently. The spiral pattern concentrates gas and dust into dense regions where gravity can work its magic most effectively. The arms act as cosmic assembly lines, gathering raw materials and processing them into stars, planets, and the heavy elements that make rocky worlds possible. They're not just beautiful structures, but engines of galactic change, shaping the character and destiny of everything within their embrace. As we drift through our quiet arm tonight, carried along at hundreds of thousands of kilometers per hour in our galactic orbit, we're participants in this ancient dance. The spiral structure surrounds us, the density waves organize our neighborhood, and the cosmic recycling that builds new worlds from stellar ashes flows through the space around us. We're woven into the galaxy's rhythm as surely as the stars themselves. And within these sweeping arms, in patches where gas grows dense and gravity begins its patient work, something magical is always beginning, the first bright breath of a newborn star, those sweeping spiral arms we traced through. Radio waves and hydrogen whispers are far more than elegant patterns etched in starlight. They are the galaxy's workshops, cosmic assembly lines where the most fundamental acts of creation unfold on scales that dwarf imagination. If you could drift through one of these arms in a vessel that traversed light years like city blocks, you would witness the Milky Way at its most creative and generous, transforming simple hydrogen into the complex elements that make worlds and life possible. As you approach a spiral arm from the quieter spaces between, the change is gradual but profound. Wisps of gas grow thicker, vast molecular clouds that span hundreds of light years, yet remain almost empty, their interiors colder than the space between planets. These are the raw materials of creation, hydrogen molecules drifting in the cosmic dark, waiting for the gentle nudge that will awaken them. When a spiral density wave sweeps through, compressing these clouds like a slow-motion tide, gravity begins its patient work. Invisible threads of increased density draw more gas inward, starting a process that unfolds over millions of years, but whose outcome is written in the physics of collapse and heat. Within these compressed regions, the first signs of stellar birth appear as dark knots against the faint glow of scattered starlight. These are protostars, not yet true suns, but promises gathering mass and warming as they shrink. Around each condensing core, a spinning disk of gas and dust forms, the birthplace of future planets. If you could watch in cosmic time-lapse, you would see these disks develop gaps and lanes where worlds are clearing their orbital paths, like rings in a pond marking the passage of unseen swimmers beneath the surface. Then comes the moment of ignition. When the core grows hot and dense enough, nuclear fusion begins. Hydrogen transforms into helium, mass converts to energy, and a new star takes its first steady breath. The transformation of the surrounding region is immediate and spectacular. The most massive newborns blaze with temperatures so extreme they appear blue-white even from thousands of light years away. Their fierce ultraviolet radiation floods the molecular cloud, stripping electrons from hydrogen atoms and causing the gas to glow with the soft pink light of ionized hydrogen. These glowing regions emission nebulae like our nearby Orion Nebula or the distant Eagle Nebula with its towering pillars are more than beautiful. They are announcements that a stellar nursery has opened for business. Within their colorful embrace, clusters of stars emerge together like cosmic families, bound temporarily by their shared origin and mutual gravity. The massive blue giants burn brilliantly but briefly, exhausting their nuclear fuel in just a few million years. When they die, they don't fade quietly but explode as supernovae, detonations so powerful they can briefly outshine entire galaxies. These stellar explosions are not endings but transformations. Everything the massive star created during its lifetime, carbon forged in its core, oxygen from helium fusion, iron from the final desperate moments before collapse, scatters into space at thousands of kilometers per second. The expanding shock waves from these explosions compress nearby gas clouds, often triggering the next generation of star formation in an endless cycle of birth, death, and renewal. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in stellar furnaces and scattered by these cosmic recycling events. The spiral arms serve as highways for this creative process, channeling gas flows along magnetic field lines that stretch for thousands of light years. Stars born within the arms don't remain fixed there, but follow their own orbital paths around the galactic center. The most massive stars live and die within the arm where they formed, their brief lives illuminating the spiral structure. Smaller, longer-lived stars like our Sun can drift through multiple arms over their billion-year lifetimes, carrying their planetary systems through changing galactic neighborhoods. Our home in the Orion Arm represents a fortunate balance in this cosmic ecosystem. We're active enough to benefit from the heavy elements created by previous generations of massive stars, yet calm enough to avoid the intense radiation and frequent explosions that might sterilize planetary surfaces. The stellar nurseries around us, like the Orion Nebula visible to your naked eye, are smaller and more scattered than those in the galaxy's major arms. This moderation may be crucial for life's development, providing the ingredients for complex chemistry while allowing billions of years of stable evolution. As you rest tonight, these processes continue around us. Within a few thousand light-years of where you lie, new stars are condensing from gas clouds. Massive suns are approaching their spectacular finales, and the elements that will become future worlds are being scattered into space. The spiral arms are not ancient history but ongoing story, and we are characters within it, made from stellar ashes, warmed by nuclear fire, drifting through the galaxy's creative embrace. But these luminous arms and their stellar neighborhoods exist within something far more mysterious, a vast architecture that extends beyond what telescopes can see. To understand what holds this entire cosmic dance together, we must journey toward the hidden heart where all the galaxy's motion finds its anchor, where something invisible and immense waits in the direction of Sagittarius, veiled by curtains of cosmic dust. The spiral arms, with their stellar nurseries, all curve inward towards something that remains tantalizingly hidden, something that anchors the entire galactic dance, yet refuses to show its face to our eyes. When you look toward the constellation Sagittarius on a warm summer evening, you're gazing in the direction of the Milky Way's heart, where the band of light swells thickest and brightest across the sky. Yet paradoxically, even though this is the most important region of our galaxy, the gravitational center around which everything orbits, we cannot see it directly. The reason is both simple and profoundly frustrating: dust. Between us and the galactic center stretches an invisible veil, thousands of light-years of microscopic particles scattered by stellar winds and supernova explosions across billions of years. This cosmic soot absorbs and scatters visible light so effectively that peering toward Sagittarius is like trying to see through thick fog. The brilliant core that should dominate our night sky is reduced to a subtle brightening, its secrets locked away behind curtains of interstellar dust that no ordinary telescope can penetrate. The light we do glimpse from that direction carries an almost mystical quality when you consider its journey. That glow began its trek toward us roughly 26,000 years ago, when humans were painting on cave walls and the great ice sheet still covered much of the northern continents. Every photon reaching your eyes tonight is an ancient messenger carrying news from the galaxy's heart as it existed in humanity's deep prehistory. We see not the galactic center as it is, but as it was when our species was just beginning to dream of the stars. Only when astronomers learned to see beyond visible light did this hidden realm begin to reveal its secrets. Infrared telescopes detecting the longer wavelengths that slip through dust like whispers through a keyhole showed stars blazing where none had been visible before. Radio telescopes tuned to specific frequencies revealed swirling gases and magnetic fields threading through the darkness. X-ray observatories caught high-energy flashes from matter heated to millions of degrees. Each new wavelength was like opening another window in a previously sealed room, slowly illuminating what had been invisible. What these instruments revealed was breathtaking. Behind the dust lies a stellar metropolis unlike anywhere else in the galaxy, a dense bulge where hundreds of millions of ancient stars crowd together in a roughly spherical swarm. If you could somehow transport yourself there, your night sky would blaze with hundreds of bright neighbors, so many that reading by starlight would be not only possible, but comfortable. These are among the galaxy's oldest residents, yellow and red suns that have burned steadily for billions of years, their accumulated light creating a warm glow that would banish true darkness forever. But the most extraordinary discovery wasn't what astronomers could see, but what they could infer from careful observation. Stars near the very center were moving at incredible speeds, whipping through tight elliptical orbits in patterns that defied explanation. Some of these stars, catalogued simply as S-stars for their proximity to the core, complete their entire orbits in just a few decades, reaching velocities that stretch the boundaries of physics. Their paths curve so sharply and their speeds climb so high that only one explanation fits the observations. They're dancing around a supermassive black hole, a gravitational monster containing the mass of 4 million suns compressed into a region smaller than our solar system. This invisible anchor, designated Sagittarius A star, holds the entire galaxy in its gravitational embrace while remaining forever hidden behind an event horizon where space and time themselves break down. It is both nothing and everything, absent from our sight yet present in every stellar orbit, including our own gentle path around the galactic edge. In 2022, human ingenuity achieved something remarkable. The Event Horizon Telescope, a planet-spanning network of radio dishes working in perfect synchronization, captured an image of this invisible giant. Not the black hole itself, which by definition cannot be seen, but the shadow it casts against the glowing materials spiraling toward its edge. The photograph shows a perfect ring of light bent by extreme gravity, surrounding absolute darkness. For the first time, humanity glimpsed the silhouette of the monster at our galaxy's heart. Yet, this black hole is not a destroyer, but a creator of cosmic order. Its immense gravity provides the central mass that binds the Milky Way together, the anchor point around which spiral arms maintain their graceful curves and stars, like our sun, follow their patient orbits. Without this hidden presence, the galaxy as we know it could not exist. The arms would unwind, stellar paths would decay, and the beautiful structure we call home would dissolve into chaos as you rest tonight. Remember that you're part of this ancient gravitational dance, moving at hundreds of thousands of kilometers per hour in a vast orbit around something you cannot see. The ground beneath you, the air around you, every atom in your body responds to the pull of that distant heart, following paths carved by invisible influence across the cosmic dark. We are all of us held in place by gravity's patient grip, dancing around mystery itself. The hidden heart beats with gravity's rhythm, and in that steady pulse, the entire galaxy finds its time. But what exactly is this gravitational anchor that shapes our cosmic destiny? What strange physics governs a place where matter disappears forever, yet somehow holds everything together? That gravitational anchor we discovered hidden behind cosmic dust, the invisible giant that holds our entire galaxy in its patient embrace, deserves to be understood not as a cosmic monster but as something far more profound. Astronomers call it Sagittarius A star, a modest name that conceals one of the universe's most extraordinary objects, a supermassive black hole whose very existence challenges our understanding of space, time, and reality itself. Yet for all its strangeness, this invisible heart beats with the rhythm that keeps our cosmic home stable and safe. To grasp what Sagittarius A star truly represents, imagine pressing a heavy sphere into the center of a stretched rubber sheet. The weight creates such a steep depression that marbles rolled nearby spiral inward, unable to escape once they cross a certain boundary. A black hole works similarly, except the sheet is the fabric of space and time itself, warped so severely that nothing, not even light, can climb back out once it falls too far inward. This boundary, called the event horizon, stretches roughly 25 million kilometers across for our galactic center, enclosing the mass of 4 million suns compressed into a region smaller than Mercury's orbit around our sun. The discovery of this invisible giant represents one of astronomy's greatest detective stories. Since black holes emit no light, astronomers had to become cosmic detectives, watching for clues in the behavior of nearby stars. For decades, they tracked individual suns orbiting the galactic center, measuring their positions with incredible patience as they swept through their elliptical paths. Some of these stars, catalogued simply as S-stars, complete their entire orbits in just 16 years, reaching speeds of thousands of kilometers per second as they whip around the unseen mass like cosmic race cars on an invisible track. These stellar dances became laboratories for testing Einstein's predictions under the most extreme conditions imaginable. As the stars approach closest to the black hole, their light stretches and reddens in the intense gravitational field, exactly as theory predicted a century ago. Their orbital paths trace perfect ellipses that precess slightly with each passage, creating rosette patterns that match mathematical calculations with stunning precision. In 2020, the scientists who tracked these stellar choreographies were awarded the Nobel Prize in Physics, recognition for proving beyond doubt that a supermassive black hole lurks at our galaxy's heart. Despite its immense power, Sagittarius A star is remarkably well behaved by cosmic standards. Unlike the ravenous monsters that power distant quasars, blazing so brightly they outshine entire galaxies, our galactic center remains relatively quiet. It feeds slowly and sporadically, consuming only occasional wisps of gas or the rare star that ventures too close. Most of the time it slumbers peacefully, glowing faintly in radio waves and infrared light, a gentle giant whose restraint may be crucial for life. Throughout the galaxy, this cosmic temperance allows star formation to proceed undisturbed throughout. The Milky Way's spiral arms, creating the stable environment necessary for planets like Earth to develop and maintain life over billions of years. We are fortunate to orbit a supermassive black hole that exercises its tremendous power with such remarkable restraint, providing gravitational order without destructive outbursts. In 2022, human ingenuity achieved something extraordinary. The Event Horizon Telescope, a planet-spanning network of radio dishes working in perfect synchronization, captured humanity's first image of this invisible giant. Not the black hole itself, which by definition cannot be seen, but the shadow it casts against glowing material spiraling toward its edge. The photograph revealed a perfect ring of superheated plasma bent by extreme gravity, surrounding absolute darkness, visual proof of Einstein's most exotic predictions made real. Perhaps most remarkably, this cosmic giant occasionally flickers. Infrared telescopes catch brief flares as clumps of matter heat up during their final moments before disappearing forever across the event horizon. These gentle bursts remind us that the black hole is not static but dynamic, constantly maintaining the precise gravitational balance that keeps our galaxy's spiral structure intact across billions of years. As you rest tonight, 26,000 light-years from this invisible anchor, you might find comfort in knowing that something so alien can also be so essential to our existence. Without Sagittarius A star's gravitational embrace, the Milky Way would not maintain its elegant spiral arms. The orderly rotation that carries us safely through space would dissolve into chaos. We orbit this mystery not as prisoners but as beneficiaries of its organizing influence, held in stable patterns that have persisted since long before Earth formed. The black hole that could theoretically destroy anything venturing too close instead creates the framework within which billions of stars shine, planets form, and life flourishes in the galaxy's quieter neighborhoods. At the center of our cosmic home lies not destruction, but the foundation of cosmic order, invisible yet indispensable, alien yet essential to everything we know and are. This realization brings us to an even more profound question. If such an immense object governs our galaxy from its hidden heart, how do we measure the true extent of its domain? How do we grasp distances so vast that even light, the fastest messenger in the universe, requires tens of thousands of years to carry news across the spans we call home? That invisible giant at our galaxy's heart governs a domain so vast that ordinary measures collapse into something approaching poetry. To understand how far Sagittarius A*'s gravitational influence truly extends, we must learn to speak the universe's native language for distance, a strange tongue that weaves time and space together until they become inseparable. When astronomers say our galaxy stretches 100,000 light-years from edge to edge, they're not just giving us numbers. They're describing a realm where distance becomes time, where looking outward always means looking backward, and where even light itself becomes a messenger from the deep past. A light-year sounds like it measures time, but it measures distance, the span that light travels in one Earth year. To grasp this cosmic yardstick, start with light's incredible velocity, nearly 300,000 kilometers every second. In the time your heart beats once, a photon could race around our entire planet more than 7 times. This is the universe's ultimate speed limit, making everything we experience in daily life feel like standing perfectly still. Now let that rhythm expand in your mind. Take those 300,000 kilometers per second and multiply by 60 seconds in a minute, then 60 minutes in an hour, then 24 hours in a day, then 365 days in a year. The result is almost 10 trillion kilometers, a number so large it stops feeling like mathematics and becomes more like a whispered secret. That incomprehensible span is 1 light year, just one step on the cosmic distance ladder. When we say the Milky Way stretches 100,000 light-years across, we're describing something both simple and staggering. Even light, the fastest phenomenon in existence, would need 100,000 years to cross from one galactic edge to the other. Imagine a beam departing tonight from the galaxy's far rim, racing toward us through spiral arms and stellar nurseries. By the time it arrived, human civilization would be unimaginably transformed, if it existed at all. Languages would have evolved beyond recognition, continents would have shifted through geological time, and entire epochs of history would have risen and fallen. 100,000 years encompasses more time than all of human recorded experience. This profound relationship between distance and time transforms every glance at the night sky into a form of time travel. The light reaching your eyes tonight carries news from different eras, depending on how far each photon has journeyed. That gentle brightening toward Sagittarius, marking our galaxy's hidden heart, began its trek 26,000 years ago when ice sheets covered northern lands and humans were painting the first animals on cave walls. The light from nearby stars shows you their faces from just a few years past, practically the present in cosmic terms. More distant suns reveal themselves as they appeared decades, centuries, or millennia ago, when entirely different human societies flourished on Earth. This means the Milky Way you see doesn't actually exist as a single moment. It's a temporal collage assembled from light that departed different regions at different times. Some stars show you the cosmic equivalent of yesterday, others display their medieval appearances, still others reveal their ancient faces from humanity's prehistory. The galaxy we think we observe is part current, part historical, part archaeological, a living museum where every age of stellar evolution remains simultaneously visible. Even our nearest stellar neighbor illustrates these mind-bending scales. Proxima Centauri lies just 4.2 light-years away, our closest cosmic companion beyond the Sun. Yet even this relatively tiny gap would take our fastest spacecraft tens of thousands of years to cross. The journey to our nearest neighbor is as unreachable within human lifetimes as crossing the entire galaxy itself. To map these immense distances, astronomers have built an ingenious ladder of measurement techniques. The first step uses parallax, watching how nearby stars shift slightly against the background as Earth swings around the Sun. Measure that tiny wobble carefully, and geometry reveals the distance. For stars too far for parallax, astronomers rely on standard candles like Cepheid variables, pulsating stars whose steady rhythms reveal their true brightness. Compare how bright they appear to how bright they actually are, and their distance emerges from the mathematics like a coastline appearing through lifting fog. The temporal isolation created by these distances has profound implications. If a civilization existed on the galaxy's far side, any message they sent would take 100,000 years to reach us. By the time we received their greeting, their entire species might have evolved beyond recognition or vanished entirely. Our reply would require another 100 millennia to arrive. Meaningful conversation becomes impossible across the galaxy's breadth, making each stellar system an island in an ocean of space and time. Yet this apparent isolation offers an unexpected gift. Every time you look up, you're gazing directly into the galaxy's biography, witnessing its entire history written in starlight. The red giants show you stellar old age from decades past. Young blue supergiants display their brilliant youth from when your grandparents were young. Ancient globular clusters reveal the galaxy's childhood from more than 10 billion years ago. Between these extremes, every epoch of galactic evolution remains on display, preserved in light that has traveled unimaginable distances to reach your eyes. To help your mind hold these scales, imagine shrinking the Milky Way to the size of a dinner plate. Our entire solar system would be smaller than a grain of salt near the edge. The distance to the nearest star would be another microscopic crystal beside it. Even this toy model carries a warning. Shrinking the numbers makes them feel manageable, but it cannot tame the reality that our home is vast in ways that resist all domestication. As you rest tonight, carried along at hundreds of thousands of kilometers per hour in your galactic orbit, remember that you exist in a universe where distance and time interweave completely. The light reaching you connects you to the galaxy's deep past, while light leaving Earth tonight will carry news of this moment to distant stars for thousands of years to come. In this cosmic perspective, every glance becomes history, every moment becomes eternal, and every distance becomes a journey through time itself. But if light requires such immense spans to cross our galaxy, where exactly do these vast reaches end? Does the Milky Way have clean boundaries where stars simply stop? Or does it fade gradually into something larger and more mysterious than we've yet imagined? If light requires such immense spans to cross our galaxy, weaving distance and time together in ways that challenge imagination, then the question of where these vast reaches actually end becomes surprisingly slippery. You might picture the Milky Way as a great island in space with clear shores where stars simply stop and emptiness begins. But when you travel outward in your mind, following those ancient photons toward whatever boundary awaits, the starlight doesn't end so much as fade, like morning mist rising from a lake, dense at the center and gradually thinning until you can no longer say precisely where galaxy becomes void. A familiar disk we see as that gentle river of light overhead represents just the most obvious part of our cosmic home. This spiral structure, with its arms threading through space and stellar nurseries glowing softly in the darkness, does indeed stretch roughly 100,000 light-years from edge to edge. But even this seemingly solid boundary requires choices about where to draw lines through gradually diminishing stellar populations. The disk's edges are ragged and warped, like a well-worn record slightly bent by time, with stars thinning rather than stopping abruptly. Some astronomers count until stellar density drops below a certain threshold. Others extend the measurement to include the last detectable gas clouds, or trace the orbital paths of the outermost known stars. Each method yields slightly different answers, which is why you might encounter measurements ranging from 100,000 to 150,000 light-years for what appears to be the same structure. Beyond this visible disk lies something far more extensive, yet nearly invisible, the stellar halo, a vast spherical region filled with ancient stars and globular clusters that drift high above and below the spiral arms like lanterns hung in three-dimensional space. These stellar fossils from the galaxy's earliest epochs follow elongated paths that carry them hundreds of thousands of light-years from the galactic center, far beyond the disk's apparent edge. Some clusters contain hundreds of thousands of ancient suns packed into glittering spheres. Others have been shredded by gravity over billions of years, leaving long, faint streams that wrap around the galaxy like ghostly rivers. If you include this halo in your definition of the Milky Way, our galaxy suddenly triples in size, stretching perhaps 300,000 light-years across. But even that expanded boundary fails to capture the galaxy's true extent. Surrounding everything we can see lies the most substantial component of all, the dark matter halo, an invisible cloud of mysterious particles that outweighs all the visible stars by perhaps 5 or 10 times. This unseen architecture extends much farther still, reaching perhaps 1,000,000 light-years from the galactic center, its outskirts already mingling with similar halos around neighboring galaxies like Andromeda. We detect this invisible bulk only through its gravitational influence, watching how stars and gas move faster than they should if only visible matter were present. These nested layers create a cosmic puzzle. Which boundary defines the real Milky Way? The answer depends entirely on what you choose to count. Focus on the bright spiral arms where most star formation occurs, and you get one measurement. Include the ancient halo with its globular clusters and stellar streams, and you reach another. Account for the dark matter that actually dominates the galaxy's mass, and you arrive at a third answer entirely. The Milky Way doesn't possess a single size, but rather a series of boundaries that fade gradually into the larger universe. If you could somehow drift outward from our solar system, crossing the disk toward whatever edge you chose to acknowledge, you wouldn't encounter a moment when you suddenly left the galaxy behind. The transitions would be gradual enough that you might miss them entirely. First, the constellations would thin, clusters would grow rare, gas would give way to almost perfect vacuum. After tens of thousands of light-years turning back, you would see the Milky Way as an object for the first time, a pale disk with slight central swelling, threaded with faint curving arms. Continue outward, and eventually you'd find yourself surrounded by only occasional ancient stars or globular clusters, with the galaxy itself visible in the distance as a beautiful spiral shining against the cosmic dark. Even then, you wouldn't have truly escaped. You'd still be within that invisible dark matter halo, still bound by its gravity, still technically a resident of the galaxy's outermost suburbs. To leave the Milky Way entirely would require traveling hundreds of thousands of light-years farther than any light from Earth has yet reached, crossing distances so vast that the journey would outlast the entire history of complex life on our planet. Perhaps this ambiguity teaches us something profound about cosmic architecture. The universe prefers soft boundaries over hard lines, gradual transitions over sharp divisions. Everything connects to everything else through gravity, through shared history, through invisible threads that link galaxies into larger patterns. The Milky Way is both discrete and boundless, depending on how you choose to look at it. As you rest tonight, consider that you exist within multiple definitions of home simultaneously. You're inside the bright disk where spiral arms sweep through space, inside the ancient halo where globular clusters drift in slow orbits, and inside the dark matter cloud that extends farther than we can measure or imagine. Each layer contains you, surrounds you, claims you as its own. But if our galaxy's boundaries prove so elusive to define, how do we even begin to count the stellar population within them? How many individual suns call this vast, softly edged structure home? If our galaxy's boundaries fade so gradually into nothingness that we struggle to define where the Milky Way truly ends, then attempting to count the individual stars within those soft edges becomes an exercise in cosmic humility. When you stand beneath a truly dark sky, thousands of points of light scattered overhead might seem countless, overwhelming in their abundance. Yet every star visible to your naked eye represents millions more hidden in the darkness, too faint or too distant for human vision to detect. The gentle band of the Milky Way itself, that familiar river of light, contains more individual suns than you could tally in 1,000 lifetimes of patient counting. Imagine trying to estimate the population of a vast city while standing on a single street corner in thick fog. You can count the streetlights visible nearby, observe patterns in the density of buildings within your limited view, then extrapolate outward using mathematical models and educated guesses. But the final number remains frustratingly uncertain, a careful estimate rather than a precise census. This is exactly the challenge astronomers face when attempting to count galactic stars, armed with increasingly sophisticated instruments, yet still humbled by the sheer magnitude of what we're trying to measure. From our embedded position within the stellar forest current, estimates suggest the Milky Way contains somewhere between 100 billion and 400 billion stars. That enormous range, spanning a factor of 4, reveals just how difficult this cosmic accounting truly becomes. Whether the true count lies closer to the conservative or generous boundary, the numbers themselves transcend ordinary comprehension. If you could somehow count one star every second without pause, reaching even the lower estimate would require over 3,000 years of continuous tallying. And you would still be missing countless stars too faint for our instruments to detect across the galaxy's vast distances. The challenge deepens when you consider that most of our stellar neighbors remain essentially invisible. Red dwarf stars, small, cool suns that burn their nuclear fuel so slowly they can shine for trillions of years, comprise perhaps 3/4 of all stars in the galaxy. Yet their faintness makes them nearly undetectable beyond our immediate cosmic neighborhood. These patient embers represent the galaxy's true population, the quiet majority that shapes stellar statistics while contributing little to the overall glow. For every star like our Sun, there may be dozens of these modest red dwarfs, hidden in the cosmic shadows, yet outnumbering all other stellar types combined. At the opposite extreme shine the massive blue giants, stellar furnaces so hot they appear brilliant across the entire galaxy. These cosmic beacons burn fast and die young, exhausting their nuclear fuel in just a few million years before exploding as supernovae. Their brightness makes them visible from enormous distances, but their rarity means they contribute little to the actual stellar count. Between these extremes lies stars like our Sun, medium-sized, steady burners that represent a comfortable compromise between brightness and longevity, neither dominating the census nor disappearing into statistical insignificance. Astronomers approach this seemingly impossible task through multiple ingenious methods, each carrying its own uncertainties. They measure the total light output from different galactic regions and divide by the average brightness expected from mixed stellar populations, like estimating apartment occupancy from the glow of a distant city at night. They weigh the visible matter through gravitational studies and calculate how much mass exists in stellar form versus gas and dust. They count stars meticulously in small representative regions and extrapolate to the entire galactic volume, like polling a neighborhood to predict citywide demographics. Beyond individual stars lie the clusters, stellar cities within our galactic metropolis. Globular clusters pack hundreds of thousands of ancient suns into glittering spheres, their cores so dense that stars blur together even in powerful telescopes. Open clusters scatter younger stars more loosely through the spiral arms, temporary associations that will eventually disperse as their members drift apart. Each cluster complicates the census, representing not individual stars but stellar communities whose boundaries fade gradually into the surrounding stellar field. The counting becomes even more complex when you include stellar remnants, the ghostly remains of stars that have exhausted their nuclear fuel and ceased to shine. White dwarf stars, neutron stars, and black holes represent the endpoints of stellar evolution, invisible to most surveys, yet still gravitationally bound to the galaxy. These stellar corpses may equal the living population in number, potentially doubling the true census while remaining largely uncounted in traditional tallies of luminous objects. Perhaps the most remarkable implication of this cosmic census concerns planetary abundance. If the galaxy contains hundreds of billions of stars, and if most stars host planetary systems, as current observations suggest, then the number of worlds within our galaxy may reach into the trillions. Rocky planets, gas giants, ice worlds, and countless variations we haven't yet imagined orbit quietly in the darkness. Among them, some may reside in temperate zones where liquid water could exist, where the conditions for life as we know it might flourish on scales we're only beginning to contemplate. As you rest tonight, surrounded by this unimaginable stellar multitude, remember that every point of light you've ever noticed represents just the tiniest sample of our cosmic neighborhood. The faint band overhead contains more individual nuclear furnaces than human language can comfortably express, each one potentially warming its own family of worlds, each one part of an abundance that transforms speculation about cosmic life into sober possibility. Yet this overwhelming population of visible stars, numerous beyond all comprehension, represents only a small fraction of what our galaxy truly contains. The bulk of the Milky Way's mass remains completely invisible, composed of mysterious material that outweighs all the shining stars by factors we're only beginning to understand. To grasp what holds this vast stellar city together, we must venture beyond the comfort of the luminous and listen for what does not shine at all. Those hundreds of billions of stars we struggle to count, overwhelming in their abundance, represent only the visible surface of something far more mysterious and vast. All the stellar light that reaches your eyes tonight, every glowing nebula captured by telescopes, every bright cluster scattered through the spiral arms, together they account for less than 1/6 of what the Milky Way actually contains. The rest is invisible, detectable only through its gravitational influence, the cosmic presence so elusive that we know it exists primarily because of what it does rather than what it is. The discovery of this invisible majority emerged gradually through one of astronomy's most elegant detective stories. In the mid-20th century, astronomers began measuring how far stars orbit at different distances from the galactic center, expecting to find a simple pattern. Just as planets farther from the Sun move more slowly in their orbits, stars farther from the galactic center should likewise slow their pace according to the fundamental laws of gravity. But when Vera Rubin and her colleagues made precise measurements, they discovered something startling. Stars in the outer regions of galaxies, including our own, were moving far too fast, maintaining speeds that suggested far more gravitational pull than all the visible matter could provide. Imagine watching cars navigate a traffic circle and noticing they're all taking the curves much faster than they should, be able to manage without flying off the road. You would naturally conclude that something invisible was helping them maintain their grip, perhaps a magnetic system beneath the pavement or some other hidden influence. The galaxy presented astronomers with exactly this puzzle. Stars throughout the Milky Way were orbiting as if they felt the gravitational pull of 5 to 10 times more matter than all the visible stars, gas and dust combined. This invisible scaffolding extends far beyond the bright disk where most stars reside, forming a vast spherical halo that may stretch 1 million light-years from the galactic center. If you could somehow see this dark matter directly, the Milky Way would appear completely transformed. The familiar spiral arms and central bulge would become just a small, glowing ornament embedded within an enormous, invisible cloud, like a jeweled pendant suspended in the center of a vast, transparent sphere. What makes dark matter so mysterious is not just its invisibility, but its apparent indifference to almost everything except gravity. Unlike ordinary matter, which can collide, heat up, cool down, and form complex structures, dark matter seems to interact with itself and with normal matter only through gravitational attraction. It doesn't emit light like stars, doesn't absorb light like dust, doesn't even seem to clump together into dense objects the way ordinary matter forms planets and stars. It simply drifts through space in vast, diffuse clouds, making its presence known only through the way it bends the paths of things we can see. The evidence for this invisible bulk has accumulated from multiple independent sources, each pointing to the same remarkable conclusion. When astronomers observe how light from distant galaxies bends as it passes through space, the deflection reveals invisible mass along the path, acting like a cosmic magnifying glass. When they study how galaxies move within clusters, they find the same pattern, far more gravitational influence than visible matter can explain. The universe consistently behaves as if it contains vast amounts of matter we cannot detect directly. Within our own galaxy, the dark matter halo plays several crucial roles that make our existence possible. It provides the gravitational foundation that holds everything together. Without this invisible scaffolding, the Milky Way's spiral arms would unwind, its stars would drift apart, and the entire structure would dissolve into chaos over cosmic time. The dark matter creates a stable gravitational well within which ordinary matter can settle into the organized patterns we observe today. Perhaps most remarkably, dark matter may have provided the original framework within which all cosmic structure formed. In the early universe, before the first stars ignited, dark matter began clumping under its own gravity, creating a cosmic web of filaments and nodes. Ordinary matter, consisting of hydrogen and helium gas, fell into these invisible scaffolds, eventually cooling and condensing to form the first generation of stars and galaxies. In this sense, every star you see tonight, including our Sun, exists only because dark matter created the gravitational architecture necessary for cosmic structure to emerge. As you rest in the darkness, remember that you're immersed in this invisible ocean without knowing it. Dark matter streams through your room, through your body, through the earth itself, interacting so weakly with ordinary matter that countless particles may pass through you every second without leaving any trace. You cannot feel it, see it, or sense it directly, yet it outweighs everything visible in your cosmic neighborhood by factors that challenge imagination. This hidden majority reveals the cosmos as far stranger and more mysterious than appearances suggest, filled with invisible influences that shape everything we know while remaining fundamentally alien to our experience. The Milky Way is like a cosmic iceberg. The luminous stars and nebulae are the shimmering tip, while the dark matter halo is the vastly larger bulk beneath, unseen but utterly essential to our galaxy's stability and our own existence. But within this vast, invisible embrace drift other ancient witnesses to our galaxy's long history, visible stars and clusters, so old they remember when the Milky Way was young, scattered through a region that holds the galaxy's deepest memories and most enduring mysteries. Within that vast, invisible embrace of dark matter, scattered like ancient monuments across the galaxy's outer reaches, drift the oldest visible witnesses to our cosmic home's long history. While the spiral arms bustle with young stars and glowing nebulae, the stellar halo preserves a quieter archive, a cosmic countryside where the galaxy's deepest memories rest in starlight that has been traveling for more than 10 billion years. Think of the Milky Way not as a flat spiral, but as an enormous three-dimensional structure, like a cosmic dandelion seed head with the bright disk glowing at its heart. The halo extends this architecture hundreds of thousands of light-years in every direction, reaching far above and below the galactic plane where most stars reside. It's sparsely populated compared to our busy neighborhood, but what lives there carries stories from epochs when the universe itself was fundamentally different from the cosmos we know today. The most magnificent residents of this ancient realm are globular clusters, glittering spheres that pack hundreds of thousands of old stars into volumes so compact their combined light appears as fuzzy patches to your naked eye. Through telescopes, they resolve into breathtaking stellar cities, where individual suns crowd so closely together that the night sky would blaze with hundreds of bright neighbors if you could somehow visit their cores. These clusters are among the oldest structures in the galaxy, containing stars that formed when the universe was less than 2 billion years old before our solar system existed, before most of the heavy elements that make rocky planets possible had been forged in stellar furnaces. Unlike the orderly circular paths followed by disk stars like our Sun, these ancient clusters sweep along elongated, tilted orbits that carry them far above and below the spiral arms before returning in stately processions lasting hundreds of millions of years. They're like cosmic lighthouses, their paths mapping the true gravitational architecture of the galaxy, while their light carries chemical signatures from an era when star formation proceeded under utterly different conditions than anything we observe today. Between the clusters drift individual halo stars, ancient wanderers whose origins remain beautifully mysterious. Some formed within the Milky Way during its chaotic youth, survivors from when the galaxy was still assembling itself from smaller pieces. Others carry chemical fingerprints suggesting more exotic histories. They may be cosmic refugees, former residents of smaller galaxies that our Milky Way consumed over billions of years, their parent systems long since destroyed, but their stars preserved as permanent immigrants in our galaxy's outer reaches. This process of galactic growth has left its traces written across the halo in stellar streams, ghostly ribbons of stars that wrap around the galaxy like cosmic contrails marking the paths of destroyed companions. The most prominent of these, the Sagittarius stream, stretches completely around the sky as the scattered remains of a dwarf galaxy slowly torn apart over multiple orbits. These streams transform the apparently empty halo into a dynamic archaeological site where the galaxy's history of mergers remains visible to patient observers, each ribbon telling the story of a smaller system's final journey. The halo serves as the galaxy's memory keeper, preserving evidence of processes the busy disk has long since erased. By studying these stellar fossils, astronomers reconstruct how the Milky Way assembled itself over cosmic time, growing larger and more organized through encounters with smaller neighbors. The ancient stars reveal that our galaxy is not eternal in its current form, but has evolved continuously, accumulating mass and complexity through billions of years of cosmic cannibalism. From our embedded position deep within the disk, the halo remains largely invisible to casual observation, its treasures requiring telescopes to detect and patience to understand. Yet if you could somehow travel far enough into these outer reaches, your perspective would transform completely. The familiar band of the Milky Way would no longer arch overhead, but appear as a distant, luminous disk with spiral arms, faintly visible against the cosmic dark. You would finally see our galaxy as a single, unified object rather than the fragmented glow we observe from within its crowded neighborhoods. As you rest tonight, remember that you're held within this ancient architecture, surrounded by stellar witnesses that have watched the galaxy evolve for most of cosmic history. The halo stars have observed the slow transformation of a chaotic collection of gas and dark matter into the organized spiral structure we call home, silent guardians carrying the memory of epochs before our sun existed. These whispers from the ancient past also remind us that the Milky Way doesn't exist in isolation. The same gravitational forces that scattered stellar streams throughout the halo continue to operate today, As our galaxy maintains complex relationships with a family of smaller companion systems that orbit nearby, some dancing at safe distances, others destined for eventual absorption into our ever-growing cosmic home. Those stellar streams threading through our ancient halo tell stories of smaller galaxies consumed over billions of years. But this process of galactic growth hasn't ended with the distant past. Even now, the Milky Way maintains a complex family of companion galaxies that orbit our larger structure like cosmic children, some dancing at comfortable distances while others spiral inexorably inward toward eventual absorption. These companions transform our galaxy from a solitary island into the central hub of a gravitational neighborhood where matter flows between systems and smaller structures merge into larger ones across cosmic time. The most famous members of this cosmic family shine visibly from southern latitudes. The large and small Magellanic Clouds, two irregular patches of light that have guided sailors across Earth's oceans for countless generations. To ancient mariners, they appeared as detached fragments of the Milky Way itself, celestial lighthouses marking directions across vast waters. Indigenous peoples of the Southern Hemisphere wove them into creation stories and seasonal calendars, recognizing their steady presence as part of the cosmic order. Modern astronomy reveals them as independent galaxies in their own right. The Large Magellanic Cloud, containing roughly 30 billion stars, and the Small Magellanic Cloud, hosting about 3 billion, substantial cosmic cities that appear modest only when compared to our galaxy's hundreds of billions of suns. These cloudy companions aren't passive ornaments but active participants in an ongoing gravitational ballet. As they orbit the Milky Way, tidal forces have drawn streams of hydrogen gas between them, creating the vast Magellanic Stream that stretches across the southern sky like a cosmic river, connecting the clouds to each other and eventually to our galaxy's outer reaches. This streaming gas represents raw material slowly being transferred from smaller systems to larger ones, a gentle form of cosmic cannibalism that demonstrates how galaxies grow through patient consumption of their neighbors. Much closer to home, another companion illustrates the ultimate fate awaiting systems that venture too near our gravitational embrace. The Sagittarius dwarf galaxy, though containing several billion stars, has been so thoroughly disrupted by tidal forces that it barely maintains its identity as an independent system. Its stars have been stretched into those long ribbons we discovered threading through the halo, marking the slow dissolution of what was once a coherent galactic structure. Each orbit brings further disruption, scattering more stellar refugees into our expanding halo, while the dwarf galaxy's core grows smaller and fainter. Beyond these prominent examples lies a more extensive family of ultra-faint companions, systems so dim they remained hidden until sophisticated surveys revealed their subtle presence scattered throughout our galactic neighborhood. The Fornax and Sculptor dwarf galaxies orbit far enough from the Milky Way to preserve their integrity, though they contain only a few million stars each, cosmic villages compared to our galactic metropolis. Even more elusive are the ultra-faint dwarfs discovered in recent decades, ghostly structures containing only thousands of stars spread across volumes comparable to globular clusters. These may be surviving remnants of the first generation of galaxies that formed in the early universe, preserved like cosmic fossils within our dark matter halo. Each companion galaxy tells part of the story of how cosmic structures form and evolve. The more massive systems like the Magellanic Clouds demonstrate how galaxies can maintain complex relationships over billions of years, exchanging material while preserving distinct identities. The disrupted systems like Sagittarius reveal the patient processes by which larger galaxies grow through accretion. The ultra-faint dwarfs preserve evidence of conditions in the early universe when star formation proceeded under radically different circumstances than we observe today. From our embedded perspective within the Milky Way, These companions appear as faint smudges requiring telescopes to study in detail, yet their presence profoundly influences our galaxy's structure and evolution. The gravitational pull of the Magellanic Clouds may help maintain our spiral arm patterns, while the ongoing absorption of smaller systems adds mass and complexity to our cosmic home. Every stellar stream in the halo represents a former companion whose individual identity has been erased, but whose substance enriches our galactic neighborhood. This cosmic family portrait reveals that galaxies exist not in isolation, but as interconnected communities bound together by gravity and shared history. Our companions orbit within the vast, dark matter halo we explored earlier, their motions shaped by invisible influences that extend far beyond the visible galaxy. Together with the great Andromeda spiral and the smaller Triangulum galaxy, we form the local group, a modest cluster of galaxies where the same processes of merger and growth that created our stellar streams continue to unfold on ever larger scales. As you rest tonight, remember that dozens of smaller galaxies share our cosmic neighborhood, some visible to careful observers, others hidden yet detectable through their gravitational influence. We exist within a dynamic gravitational ecosystem where boundaries between galaxies blur across cosmic time, where the patient dance of orbital mechanics slowly reshapes entire stellar populations. But beyond these modest companions, something far more dramatic approaches through the darkness, another great spiral galaxy growing slowly but inevitably larger in our sky, carrying the promise of the most spectacular merger our galactic neighborhood will ever witness. Those smaller companions dancing their orbital ballet around our cosmic home represent just the gentlest movements in a far grander choreography already unfolding. Beyond the Magellanic Clouds, beyond the scattered dwarf galaxies slowly surrendering their stars to our gravitational embrace, another participant approaches through the darkness, not a modest companion destined for absorption, but an equal partner in what will become the most spectacular transformation our galactic neighborhood has ever witnessed. In the constellation Andromeda, visible as a faint smudge to your careful eye on the darkest nights, shines our galaxy's ultimate destiny. This distant glow represents the Andromeda Galaxy, a majestic spiral even larger than our own Milky Way, containing perhaps 1 trillion stars arranged in elegant arms that sweep across more than 200,000 light-years of space. What appears as merely another nebulous patch to casual observation carries within its light a patient certainty that will reshape everything we know about our cosmic home. Andromeda lies approximately 2.5 million light-years away, making it the most distant object visible without telescopic aid. Yet this seemingly vast separation shrinks with cosmic perspective when you realize that our neighbor approaches at roughly 110 kilometers every second, closing the gap with the patient inevitability of gravity itself. In approximately 4 to 5 billion years, these two galactic giants will meet in an encounter that has already begun in the most fundamental sense. Their dark matter halos, those invisible scaffolds we discovered extending far beyond each galaxy's visible boundaries, are already overlapping, creating gravitational influences that subtly affect both systems across the cosmic void. The word collision naturally evokes images of catastrophic destruction, yet the reality will unfold as something far more subtle and beautiful than such language suggests. Galaxies consist mostly of empty space, with individual stars separated by distances so vast that direct stellar collisions will remain extraordinarily rare, even when the two systems interpenetrate completely. Instead of a cosmic crash, imagine two vast swarms of fireflies drifting through each other in a slow-motion dance that unfolds over billions of years, their patterns disrupted and reformed, while most individual lights continue to shine unharmed. What will transform dramatically is the architecture that defines both galaxies. The elegant spiral arms that currently characterize each system will stretch and distort under tidal forces, creating bridges and streams of stars like luminous taffy drawn between the merging structures. These gravitational sculptures will arch across hundreds of thousands of light-years, connecting the two systems in temporary patterns of breathtaking complexity. Gas clouds compressed by the encounter will ignite spectacular bursts of star formation, lighting up regions of space with newborn stellar nurseries far more active than anything we observe in our current galactic neighborhood. The merger will unfold as a complex choreography spanning several billion years. The galaxies will approach each other, pass through each other, separate temporarily as gravity pulls them back together, then merge again in a series of encounters that gradually dissipates their orbital energy. With each passage, the spiral structures will become more distorted until they finally dissolve completely, leaving behind a single, large, elliptical galaxy that astronomers have already named Milky Way, a smooth, football-shaped collection of stars without the dramatic arms and star-forming regions that characterize our current cosmic home. From Earth's perspective, if our planet somehow survives the Sun's evolution into a red giant star, the merger will create the most spectacular sky show in cosmic history. Andromeda will grow from its current faint smudge into an enormous structure dominating the heavens, its spiral arms clearly visible across vast portions of the night sky. During the closest approaches, the combined gravitational forces may trigger such intense star formation that the sky blazes with the light of countless stellar nurseries, a cosmic aurora painted across the entire dome of heaven. Eventually, the merged galaxy will settle into its new configuration, creating a night sky filled with the warm, diffuse glow of an elliptical galaxy's ancient stars. The merger will also reshape our solar system's galactic address in ways both profound and gentle. Currently, we orbit roughly 26,000 light-years from the Milky Way's center in the quiet Orion arm, following a nearly circular path that takes 225 million years to complete. The gravitational choreography of the merger may fling us farther from the new galaxy's center into an even quieter stellar suburb, or possibly draw us inward toward more crowded regions where the night sky blazes with hundreds of bright neighbors. Our sun's familiar orbit will likely become more elliptical and unpredictable as the gravitational landscape transforms around us. Yet the solar system itself will almost certainly survive intact, carried along like a small boat in gentle cosmic currents. Yet despite the dramatic nature of this future transformation, it represents the natural continuation of processes we've already observed throughout our galactic neighborhood. The stellar streams threading through our halo, the ongoing disruption of the Sagittarius dwarf, the slow consumption of smaller companions, all these phenomena demonstrate that galaxies grow and evolve through mergers across cosmic time. The Andromeda encounter will simply be the largest and most spectacular example of a process that has shaped our galaxy throughout its billion-year history. Far from being purely destructive, this cosmic embrace will prove profoundly creative. The compression of gas clouds during the merger will ignite new generations of stars, ensuring the continued vitality of the combined galaxy. Ancient stellar populations will find new orbits, mixing histories and blending chemical enrichments accumulated over billions of years. The supermassive black holes at each galactic center, our familiar Sagittarius A star, and Andromeda's own invisible giant, will eventually spiral inward through the combined system and merge, sending gravitational waves rippling across the cosmos like whispers in the fabric of space-time itself. As you rest tonight under stars arranged in temporary patterns that will be completely rearranged long before our sun exhausts its nuclear fuel, remember that you exist during a brief, stable interlude between cosmic transformation. The stellar streams in our halo tell stories of past mergers that built our current galaxy, while the patient approach of Andromeda writes the next chapter in an ongoing tale of cosmic growth and change. We live within a universe that tends to rearrange rather than annihilate, where endings become beginnings and where even the most spectacular transformations unfold with the gentle patience of geological time. But for now, in this quiet interval between grand cosmic gestures, we find ourselves in a remarkably peaceful corner of an ever-changing galaxy, a suburban address that has proven ideal not only for the emergence of life but for the patient contemplation of our place within these vast, slow cycles of cosmic renewal. In this peaceful interval between cosmic transformations, between the ancient collisions that shaped our galaxy's past and the distant merger that will redefine its future, we find ourselves in a remarkably fortunate location. Our solar system doesn't reside in the galaxy's bustling downtown or its sparse outer neighborhoods, but in what could best be described as a quiet cosmic suburb, the Orion Arm, a modest spur that threads gently between the Milky Way's major spiral highways like a tree-lined residential street connecting to busier thoroughfares. The Orion Arm stretches roughly 10,000 light-years along its length, making it substantial enough to host numerous stellar communities, yet narrow enough to avoid the chaotic interactions that characterize the galaxy's major arms. We orbit approximately 26,000 light-years from that hidden heart in Sagittarius, positioned in what astronomers call the galactic habitable zone, far enough from the core to escape its intense radiation and frequent stellar disruptions, yet close enough to benefit from the heavy elements forged by earlier generations of massive stars. This cosmic address proves far more significant than its humble designation might suggest. The galactic center, for all its gravitational majesty, bustles with dangers that would challenge any developing world. Stars crowd so densely there that gravitational interactions frequently disrupt planetary systems, while radiation levels climb high enough to threaten the delicate chemistry that life requires. The galaxy's outer rim offers the opposite problem: too little activity, too few heavy elements, insufficient stellar density to enrich the interstellar medium with the carbon, oxygen, and iron that rocky planets need. Our Orion Arm provides the perfect balance, like finding the ideal temperature in a cosmic Goldilocks story. It's active enough to supply the chemical ingredients for complex worlds, yet stable enough to allow billions of years of undisturbed evolution. The stellar nurseries around us, the Orion Nebula visible to your naked eye, the Eagle Nebula with its towering pillars of creation, represent gentler workshops of star formation compared to the massive, violent factories in the galaxy's major arms. From our embedded perspective within this galactic suburb, the night sky reveals our location's character through familiar landmarks. When you look toward Sagittarius during summer evenings, you're gazing inward through the Orion Arm toward the galaxy's crowded heart, which explains why the Milky Way swells brightest in that direction. Turn toward Orion in winter, and you're looking outward through our local arm toward the galaxy's edge, where the stellar population thins and the band appears fainter and more scattered. Our solar system travels through this neighborhood at nearly 828,000 kilometers per hour, yet this tremendous speed feels perfectly motionless because everything nearby moves together in the same gravitational current. We complete one circuit around the galactic center every 225 million years, a galactic year so vast that our Sun has completed only about 20 such orbits since its formation. During each of these immense cycles, continents drift across Earth's surface, entire branches of life bloom and fade, and civilizations rise and vanish while we maintain our steady path through the cosmic suburbs. Even our immediate surroundings reflect this theme of gentle balance. We drift within the local bubble, a cavity of thin, hot gas carved by ancient supernovae hundreds of light-years away. This cosmic clearing, stretching roughly 300 light-years in diameter, provides additional shelter from the denser interstellar medium that fills other regions of the galactic disk. It's like living in a park within our already peaceful neighborhood, an extra layer of cosmic tranquility. The stellar neighbors visible in our night sky, Alpha Centauri, Sirius, Vega, and hundreds of others within 50 light-years, represent the closest residents of this galactic suburb. They're near enough to study in detail, yet typical of the stellar populations that characterize spiral arm environments throughout the universe. These local stars have provided the navigational beacons and inspiring patterns that have guided human imagination for millennia, creating a night sky rich enough to spark wonder, yet stable enough to remain familiar across generations. As you rest tonight in this quiet corner of the galaxy, remember that our suburban address represents more than mere cosmic geography. The Orion Arm has provided the stable, enriched environment necessary for rocky planets to form, for complex chemistry to develop, and for life to emerge and flourish across geological time. We exist in a neighborhood that balances activity with tranquility, offering both the resources necessary for complexity and the patience required for its gradual development. From this perfect vantage point, we've managed to map our galaxy's structure, discover its invisible components, and trace its history across billions of years. Yet our embedded perspective also limits us, preventing us from seeing our cosmic home as the unified whole it truly represents. We are both inside the galaxy and partially blind to its complete form, like residents trying to sketch their city's full layout from a single street corner. To complete our journey through the Milky Way's immensity, we must step outside in imagination and glimpse what we can never observe directly, our galaxy as it appears from the vast darkness beyond its boundaries, whole and luminous against the cosmic night. From our peaceful address in the Orion Arm, we've mapped our galaxy's hidden architecture and traced its ancient history. Yet our embedded perspective has always denied us the one view that would complete our understanding. To truly grasp the Milky Way's wholeness, we must take a final journey in imagination, drifting outward through the dark matter halo, past the farthest globular clusters, into the vast emptiness between galaxies, where we can turn and see our cosmic home as it truly is, complete, luminous and whole against the infinite dark. Imagine floating in that perfect silence, hundreds of thousands of light-years from the nearest star, surrounded by darkness so profound it makes the deepest earthly night seem bright. From this impossible vantage point, the Milky Way appears as it can never be seen from within, a magnificent spiral galaxy stretching 100,000 light-years across, its arms curving outward from a golden central bulge like cream stirred slowly into cosmic coffee. The view transforms depending on your angle of observation. From above, our galaxy reveals itself as an elegant pinwheel, 4 major arms sweeping through space in graceful arcs, threaded with the pink glow of stellar nurseries and the blue light of young, massive stars. Dark lanes of cosmic dust trace delicate shadows between the arms, the same veils that hide the galactic center from our earthbound eyes. From the side, the Milky Way appears as a thin, luminous line with a bright central swelling, delicate as a horizon, yet containing everything we know. Around this luminous disk, faint as scattered diamonds, globular clusters trace their ancient orbits through the halo like cosmic fireflies. Stellar streams, those ghostly ribbons we discovered threading through space, loop and arc across the darkness, silent testimony to smaller galaxies consumed over billions of years. The entire structure breathes with slow motion, arms rippling as density waves pass through them, new stars flickering to life while others fade into stellar remnants. From this external perspective, our solar system vanishes completely, lost among hundreds of billions of other stellar points scattered throughout the spiral pattern. The Orion Arm, where we make our home, appears as just one modest spur branching between larger structures. Our sun, so central to our existence, becomes utterly anonymous, one spark among the multitude, its planets undetectable, its story unknown to any cosmic observer floating in the intergalactic void. Yet this view from everywhere and nowhere reveals something profound about existence itself. The Milky Way is simultaneously magnificent and ordinary, unique and typical. In every direction, similar spirals shine at various distances, each containing hundreds of billions of stars, each potentially harboring countless worlds where other forms of consciousness might contemplate their own cosmic homes. Our galaxy, for all its grandeur, is both special because it contains us and unremarkable among the billions of others scattered throughout the universe. This dual perspective captures something essential about our cosmic situation. From within the galaxy, we are embedded participants, our understanding built gradually through patient observation and ingenious inference. From outside, we become cosmic observers, seeing the whole pattern but losing connection to the individual stories unfolding within it. Both viewpoints are necessary, both incomplete, both true in their own way as you drift back from this imaginary vantage point, returning through the invisible dark matter scaffolding, past the ancient stellar streams, through the spiral arms where new stars kindle in glowing nurseries. You're coming home to the only perspective that truly matters, your own embedded experience within this vast structure. The gentle band of light arching across your night sky may be just the cross-section of one galaxy among billions, but it's also the backdrop of every human story, the canvas on which our species has painted its dreams for millennia. The Milky Way is both incomprehensibly vast and intimately personal. It contains more stars than human language can comfortably express, yet it also contains the one star that warms your face each morning. It stretches across distances that light requires 100,000 years to traverse, yet it provides the familiar constellations that have guided human navigation and imagination since our species first looked up in wonder. Tonight, as you rest beneath this vast architecture of stars and dark matter, remember that you are not separate from the galaxy but woven into its very fabric. The calcium in your bones was forged in stellar furnaces, the iron in your blood scattered by supernovae, the oxygen you breathe created in the nuclear hearts of massive suns. You are not merely living within the Milky Way, you are made of the Milky Way, a temporary arrangement of galactic material that has achieved the remarkable ability to contemplate its own cosmic context. The numbers we've explored together, light years and billions of stars, spiral arms and dark matter halos, can fade now like distant music as you drift towards sleep. What remains is the simple wonder of existing within something so vast, so ancient, so beautiful that human minds can barely grasp its edges. The Milky Way will continue its patient turning, carrying you through the cosmic darkness at hundreds of thousands of kilometers per hour, yet you feel only stillness, only peace, only the gentle rhythm of your breathing under stars that shine with light from the galaxy's deepest past. Thank you for wandering through our cosmic home with me tonight. The Milky Way keeps its ancient rhythm, the stars continue their eternal dance, and you, here in this moment, in this quiet corner of infinity, can simply rest. The galaxy will keep watch. Good night.